Welcome to Physics in AM. This is the Vectors coming to you live. Our today's show is brought to you by the good people at Craft. Anyways, and I just handed out equations for accelerated motion. These are the same ones you have on your sheet. We're going to learn how to use them, but I want to point out something. Now you have this on your sheet, so you're not going to copy this out. You don't have to diagram. But okay, you have a little more on your sheet too. That's what I wanted to double check. Okay. We have talked about acceleration, and you did in grade 10, as the change in velocity over the change in time. And that's the basic definition. That means it's a slope on a velocity time graph. It's velocity is the rise over run. And we've looked at that. There's that lab that you're going to get to me on Friday. Yep, let's put it down in front. So if you have a velocity time graph, you need the slope. That works, right? That's how. Then, where do these other equations come from? Do you guys remember if you do the area under a velocity graph, what do we find? Distance traveled, displacement. And guess what? If I break this up, and you don't have to write this down, but I'm just showing you these equations aren't witchcraft and stuff, they come from a place. We would have to do the area of that triangle and the area of this rectangle. And I'm showing you this because it depends if you're at university, you take physics for science majors, for like people in engineering and business majors and stuff, or if you take physics and your biology major, you don't take it for science. Anyways, where do these formulas come from? It's important if you pursue it. Well, in calculus, doing an area under a curve is called an integral. You don't have to know that yet. What is the area of the blue rectangle? When we're talking about T's and D's. Because it's space times time, you know that, right? Well, what is the height of that rectangle? Is it B1 or B2? Take a look at the blue rectangle. Yeah, B1. So this is B1, and then the T is the base, B1 and T. Plus, you're going to have to do the area of this green triangle. What is the area of that triangle? Is that? No, it isn't. Because it's got a height that's the difference of V1 and 2. V2 minus V2. Right? Half of that times the T, right? Oh. Are you? I don't know. Are you smart? I'm not going to answer that question. Anyways, okay. Now, just thinking of this. Now, this is where it comes from. I'm not going to. If you look at this part, that's something to determine. If you inserted A, and I'm not going to go through it, you don't have to memorize this stuff. The change in speed, well, that's just the green thing there on the height, right? And if I just inserted, let me do this over here. I'm going to erase this. You don't have to copy this now. I'm showing you this. 1/2, and then it's height, V2 minus V1, times the time, right? That's half of the trash. Okay. Now, if you inserted that from this formula, delta V, that's V2 minus V1, is equal to AT. You guys follow that? Insert that. I got 1/2 A T, and then the T that's already behind this. That's where the T is. area as well. That's one way of thinking of this formula. Anyways, that's where that comes from. I'm going to just quickly explain them also from this graph. If I make a red rectangle, that's the V2 height. The displacement would be the area of the red triangle, V2 times T, and then subtracting what we just figured out in green. Does that make sense geometrically? Okay. Then you can sub into each formula to find the others. The other ones are I'm just explaining that they come from somewhere. You don't have to know this for me. And later on, you'll have calculus to help. There's other ways of thinking of those areas, by the way. Okay. The main thing is that we know how to use these formulas. Oh, by the way, the first formula listed here is just that formula broken up. Delta V needs to be 2 minus V1, and then just isolating for V. That's what that first one. But you have it all listed. Okay. This is what Luke was talking about this. If you think about it, it's kind of mind-blowing. An eraser's tossed 90 centimeters up in the air and then falls down. Now, Luke, what you found, you're like, of course it is. It's sort of like that surprise. Never thought of it this way. Yeah. What is the alarming thing? Zero velocity come back down. And then come back down. That is something you're going to use in a lot of these problems, and it's not explicitly stated that this velocity is zero at some point. So let's go. Okay, in this particular one, it is. I think I'm going to just draw a diagram. We're assuming straight up, no sideways motion. It costs 90 centimeters up in the air. So 90 centimeters. That makes sense, right? And then falls down. What was the initial velocity? So I suggest, okay, you're going to copy out the problem. I'll wait for a second. So it goes up 90 centimeters in the air and then falls down. I haven't given you any other information. However, we're going to assume this is on the surface of the Earth in general. And there is information given on your formula sheet. Gravity, we use 9.80, right? Meters per second squared. I have that down, right? Okay. So our acceleration. I'm going to just list this here. I make my A like an old school typewriter. You can make a regular A. I don't care. People have asked me that. It's my small case. Okay, what else do we know? We want the initial velocity V1. And we'll list some stuff like that. I'm going to put it down here where decide where it's initially thrown out of my hat, right? 90 centimeters is basically what I was doing. Yeah. Okay. That's about 90 centimeters. So that's the scenario. It had to stop at the top. So what do you know? This is why I was saying it's not explicitly stated, but what Luke was saying, once you hear it, it's like, of course it does. What is our V2 if we're just considering the up trip? Zero. I have you down as absent because I was looking for you there when you used it. I'm going to change this right now. Okay. I guess we didn't label it as a variable, but our displacement is equal to 90. So that's in centimeters. We're going to change it to meters, but a century has 100 years. There's 100 cents to $1. So you know that we'll go from centimeters. Like I'm trying to emphasize what cents means. 100, right? You divide by 100, which you can usually do in your head, right? So decimal 90. Well, we'll get going, but I don't know why you need a ruler right now. Why don't you do this? Anyways, formula has 1, 2, 3, these 4 variables, B2, D1, D, and A. So I look through this, and I see it's the one with the squares, right? This one. I can use that one. If you've got them all listed, there's always one formula that will work. So I'm going to list, oh no, it's not listed. Okay. So I'm going to go B2 squared equals B1, squared equals B2. This is the one formula that doesn't have time. Each formula is missing one of the variables, so it makes it easy to solve. Choose the right formula, and then the rest is B2 is 0, so that makes things easy. I don't have to square it. B1 is what we're looking for. 2 times, I'm going to put the negative in there, negative 9.8, 0 meters per second squared. I'm going to just scoop that over a little bit. D is, remember how I said we can't use centimeters, so I have it all in meters, 1 system division. 190. Okay. I think we know how to do this, right? Algebra? Yeah, I'm going to just multiply out the numbers. I'm going to do the calculator. Negative 2 times negative 1.8 times 1. I'll get a number for it. I'm going to put the 6, 4 really small. They're not significant digits, but I'm not going to concentrate on 6 digits. Now, unit-wise, we've got meters per second squared times meters. What are the units here at this moment? Nothing canceled out there, and that's good. Okay. Arithmetic-wise or algebra-wise, we know that we have to add, right? And that's why that minus sign was important. So the 17.6, I'll show the whole algebra. If you can skip algebra and just go to the answer kind of thing, I'm fine with that. As long as you show the initial plug-in step and maybe something in between the conceivable. Everybody's got different algebra skills. Some are just pre-calculus, some are calculus eventually, some people I understand. You got to do a square root though. I get 4.2. When I do the square root, I get meters squared second squared becoming meters per second. Now, when I do a square root like this, you have a choice. It could have been the positive or the negative answer. Why is this one the positive? And it's from your diagram. Why is this one the positive? Tell me. We can throw it up there. If I labeled negative 9.8 as my downward acceleration, positive would be. Now, I'm going to just mention something. Isn't that same math, though? I'll do it. If we had, this wouldn't be V1. If we were just saying a round trip and I catch it back in my hand at the same level, mathematically it would be like dropping something at this height, 0. Speed going down here. Guess what that final speed would be? It'd be the negative, no, well, once it's in your hand, but as it slaps your hand, what would it do? Pardon me. It would be. Mathematically, it works out to be the exact same.
Yeah, I'm just.
I know this is a thought experiment.
So, I like throw something up in the air, and it reaches 0, wouldn't it, no matter what, the force of gravity bringing it back down? So like on the height, it's basically like.
So here's the scenario. Well, let's assume this is 96.
Yeah.
It slaps my hand with the exact same speed that it left my hand, ignoring some errors. It also slaps my hand with the exact same speed if I did that, right? You agree with that? Because it comes up, stops, and then drops.
Yeah.
It doesn't matter if I just actually held it up there. You agree with that?
Yeah.
So mathematically, what I'm saying is that if I change this to V1, this to V2, all it does is put the 0 here, so V2 there, that's straight. You see how the math will be the exact same, and it'll come up, but you have to choose, in that case, the negative. It will be down the more. So, no, I was saying if it was the round trip, if I was considering the round trip. Good. Now, I'm bringing this up though because there's some where you have the diagram and you have to make a choice, and it is the negative if you do that. So make sure you have a decent diagram so you can choose the right way. Well, another one. Oh, I just did the original. Are you sure this is from our textbook here? I'm going to double check this. Because you guys it just requires a lot of practice. 55, let me see here, page 80, 81. I'm going to pause the video the first